Population growth and industrialization have led to increasing water scarcity and necessity for water reuse and desalination, as said by Arana et al. In 2018. Climate change has led to an increase in global sea level, which in turn increases the salinity of the groundwater. This causes fresh water in many areas to have increased salinity, becoming unsafe to consume. 600 million people living in coastal zones worldwide may be impacted by increases in salinity. Areas in Asia are expected to have drops in freshwater availability by the 2050s, as said by Rakib et al. In 2019. 11% of the world's population do not have access to a safe water source, while 25% do not have access to necessary sanitation, which is a total dissolved solids measurement under 200 parts per million, as said by the Center for Disease Control.
Several methods of water purification exist, but they have varying levels of efficiencies, and many of them are impractical or too expensive to run on a large scale. Thermal distillation, which involves first evaporating and then condensing the water, leaves behind the salt. This method is in operation in the arid Gulf countries and consumes substantial amounts of thermal and electrical energy, which in turn produces greenhouse gases. Distillation is not practical because the low vapor pressure of water wastes heat as a viable energy source. This is according to Alimlik et al. 2011. Membrane separation is another technology which selectively separates materials via pores and/or mini-gaps in the molecular arrangement of a continuous structure and is being used currently in order to increase the world's quickly dwindling supply of water. Accounting for 53% of global desalination technologies, this mechanism also consumes large amounts of energy and requires capital investment. Sally de Messi et al. 2019. Unlike these pre-existing methods, biodesalination does not require a large amount of energy, nor is it too costly, according to Sally de Messi et al. 2019. Biodesalination is the process that removes excess salt from water in order to obtain fresh water suitable for animal consumption by means of a biological organism such as algae.
Halophytic algae have been used as a means of biodesalination since they have been shown to remove salt from saline soils effectively. Some halophytic algae isolate salt within the vacuoles of their tissues against the osmotic gradient, eventually converting a saline solution into a salt-free one, as said by Chen et al. In 2011. The algae Chlorella vulgaris in particular has a reputation as cost-efficient and environmentally sustainable, as said by Ido et al. In 2018.
Microbial desalination cells have been shown to be effective in the biodesalination of water. By engineering an MDC containing an anode and a cathode, the chlorine ions of salinity-induced water placed in the middle chamber flow through the ion exchange membrane into the anode, while the sodium ions flow into the cathode, according to Zamanpour et al. 2017. Wastewater is placed in the anode as it has a low electrical conductivity and can promote desalination, since this would not interfere with the charges of the anions and cations. The wastewater in the anode chamber acquires a negative charge, freeing electrons to generate a current between the electrodes. We use graphite rods through the wire connected to a resistor. In the cathode, oxygen must be reduced, gain electrons, in order to form hydroxide ions for the cathode to acquire a positive charge. This is done using algae, an efficient eliminator of carbon dioxide and biological provider of oxygen in the cathode. Electrical current is produced by the potential difference generated between the anode and the cathode due to the aerobic nature of the cathode chamber. This current allows chlorine ions to flow into the anode while sodium ions flow into the cathode.
In a paper studying desalination using the halophytic algae Schenodesmus species as well as Chlorella vulgaris, the initial salt uptake rate for Schenodesmus species during the growth phase from day 1 to day 18 was estimated using a first-order kinetics model and ranged from negative 0.015 per day to 0.0358 per day, reducing salinity up to 30%, as said in Sally de Messi et al. In 2019. In another study, a microbial desalination process was tested with the addition of the algae Chlorella vulgaris in the biocathode. Overall, sodium bicarbonate concentrations larger than 0.5 grams per liter did not have a positive effect on the performance of the microbial desalination cell, as said in Arana et al. In 2018. We hypothesized that with the addition of the algae in a microbial desalination cell, there would be a decrease in salinity while remaining healthy at a salinity of 1.5%, since a greater percentage would result in unhealthy algae, but a lower percentage would be inefficient in regards to NaCl removal. The goal of our study is to find the optimal concentration at which the algae can both remain healthy and decrease salinity most effectively.
We engineered an MDC constructed with plexiglass boxes with dimensions of 7.875 by 3.8125 by 3.875 centimeters with graphite rods as the anode and cathode connected using a copper wire with a 2500 ohm resistor. The MDC consisted of 3 chambers, an anode, a cathode, and a desalination chamber in the middle. The medium in the anode was wastewater or water that has been used and recycled after an industrial process, composed of sodium benzoate, sodium acetate, ammonium nitrate, sodium chloride, magnesium chloride, hexahydrate, calcium chloride dihydrate, and potassium phosphate dibasic trihydrate, the wastewater recipe was consistent with one from a paper by Yassine et al. In 2017 regarding the creation of synthetic wastewater.
We had 6 groups in total, 3 of which contained algae and 3 controls without algae. Different concentrations of 0%, 1.5%, and 3% salinity that are equivalent to those found in natural bodies of water were used. 0% salinity was used as a control, 1.5% salinity is the lowest amount found naturally at the mouths of rivers, and 3% is the salinity percentage of the Gulf of Thailand near Cambodia, one of the countries severely lacking in clean water. Salinity was induced using instant ocean. This is because it contains major, minor, and trace elements that are needed in marine life, creating an environment more similar to the regular ocean, as said in Solly DeMessi et al. In 2019. Chlorella vulgaris, obtained from Carolina Biological, was cultured in algal grow medium diluted with deionized water in a 1:1 ratio.
In order to determine the extent of desalination that occurred, we placed the TDS meter in the middle chamber of the MDC to measure TDS concentrations daily from day 1 to day 4. To calculate desalination percentages, we divided the final TDS measurement by the initial TDS measurement, subtracted that from 1, and then multiplied by 100. This percentage was then multiplied by the original salinity in grams per liter to determine the total removal of NaCl. The 1.5% group with algae had the highest desalination percentage of 6.7%, while the 3% group with algae had the highest removal of NaCl with 1.60 grams per liter. This trend was consistent with the findings of Saba et al. In 2016. The hemocytometer assay was conducted to show a measure of algal health. At the end of each trial, algal cells were dyed with the indicator neutral red and observed under a microscope in a hemocytometer slide. The number of cells in the 4 corner boxes were averaged and plugged into the formula. Number of cells equals 1.04 times average cells per square, all divided by 0.0001. The dilution factor of 1.04 was derived because the 1 milliliter algae solution was diluted with 40 microliters of neutral red solution. The volume of each square was 0.0001 milliliters. The 1.5% salinity group had the highest number of cells, nearly double the other 2 groups, with 325,000 cells per milliliter. This was consistent with the trends shown in a study done by Ashwani VRV and Perumal Sami N in 2017 regarding algal health. P-values were obtained by means of conducting a t-test. Although none of the values were significant and all of them were above 0.05, the values comparing groups with and without algae were 0.07 and 0.08 for the 1.5% and 3% groups respectively, suggesting that the addition of algae may have made a difference to improve desalination if we had a larger sample size.
While the 1.5% salinity appears to be the optimal concentration based upon algae health and desalination percentage, there were not enough trials to confirm if it was significantly more effective than the 3% salinity. The multimeter showed voltage fluctuating from 0 to 100 millivolts across the resistor and graphite rods in both the 1.5% and 3.0% algae groups, which compared to similar experiments done by Zamanpour et al. In 2017 and Kokabian et al. In 2015, is less than the average voltage seen in this situation, which ranged from 200 to 400 millivolts. However, due to the smaller scale of our desalination tank when compared to the desalination tanks seen in these papers, this voltage is not negligible and is most likely high enough to induce an ionic flow across membranes. Both algal groups showed a higher desalination percentage than the corresponding concentrations without algae. The difference in percent decrease in salinity relative to the control in the 1.5% and 3.0% groups respectively was 4.8% and 3.5%. Despite the trends mentioned previously that are shown in our data, the p-values are still greater than 0.05 and therefore insignificant, so we are unable to state a conclusive claim about the optimal NaCl concentration. If we were able to do this experiment over again, we would build a smaller scale microbial desalination cell. Our microbial desalination cell was very large, requiring an immense amount of materials and thus increasing the cost and going over our budget.
Over the course of our experiment, we saw a desalination percentage of 6.7 in the 1.5% salinity group and a desalination percentage of 4.7 in the 3% salinity group, both containing algae. Despite this apparent decrease in salinity, the lack of significance suggests that this study was inconclusive. We observed several trends from the data and have concluded that an optimal NaCl concentration of water that algae, Chlorella vulgaris, and an MDC can desalinate most completely while remaining healthy is a salinity likely close to 1.5%. It would be beneficial to test more salinity concentrations in the future in order to get a more complete idea of what the optimal NaCl concentration under these circumstances would be. In addition, having a greater length of time in which to do these trials would give a greater idea of the desalination percentage and NaCl removal over a period of days.